The purpose of this lesson is to look at differentiating by rules. So previously we've looked at differentiating by first principles, okay, using this nasty formula, okay, that's taking us lots of time to do differentiation. Okay, that's the hardest part, I think, substituting in the x plus h. Here's a big table of some results of differentiation. Okay, so differentiation is really finding the derivative, and we can think of it as this process going from the function to the derivative is differentiation. Alright, so this is a list of functions and their derivatives, and we want to see if we can find some patterns in here so we don't have to always differentiate from first principles using that big rule. We can just use some simplified rules. So what I want you to do is press pause and have a look through this list and see if you can come up with any understandings of some patterns or some rules that you think you can find. Alright, hopefully you've come up with a few. I think we can divide all of these and classify them as the same rule. Okay? The rule that all of these follow is that the derivative is going to be, where's my pen? The derivative is the power multiplied by the coefficient, and we reduce the power by 1. Okay, so let's have a look how this works. So probably the third one's the best one to have a look at. My original function was 5x squared. Okay, my power was 2. The coefficient, or the number, was 5. To get the derivative, I did 5 times 2, get 10, and reduce the power, which was 2, reduced it by 1 to get a power of 1. Okay, and remember, powers of 1, we're not going to write in there. We can have a look down the page. Okay, the next one is had a coefficient of 1. I multiplied 1 by 3 to get 3. Okay, coefficient by power, and then reduce this power by 1 to get 2. Okay, so all of these follow the same idea. Okay, remember the first one, x has a power of 1, so 3 times 1 gives me 3, and I really have x to the power 1 minus 1, okay, which is really x to the power 0. Okay, so the general rule here is that if my function is some constant k x to the power n, okay, then my derivative, okay, note that there's a little dash here, so it's the derivative is going to be k times n, so coefficient by the power, and x will have a power 1 less than what it was. So whatever the power was, we'll reduce it by 1. So I'll do a quick example just using the function notation. If I have a function for x to the power 7, okay, I could identify that k equals 4 and n equals 7. Okay, coefficient's 4 and the power is 7. So my derivative, okay, will be k times n, so 4 times 7. Okay, I put my variable here and subtract 1 from the power, 7 minus 1. And then I could simplify this as 28x to the power 6. Once you've done a few of these using this rule and showing it properly, by all means we expect you to just skip this step. Any questions? No? Good. Okay, going down the page, here we notice the next 4 all have a derivative of 0. Okay, so that must be something important that we can classify into a rule. having a look at all the functions on the left hand side, all of these are just constants. Okay, so our rule in words would be if the function is a constant, the derivative is 0. So what this means is if my function is just a constant, and a number, say c, okay, then my derivative is always 0. Okay, so to see this in a real example, if my function is y equals 4, then my derivative is 0. Okay, why is this the case? Because where my function is, say, y equals 4, we can see at all points on this curve, the slope is 0. Okay, so it makes sense that my slope function, my derivative function, is always 0 regardless of what the value of x is. Okay, these final examples, they all fit the same structure that we're either adding or subtracting two terms together, and our derivative is typically coming into two terms. Okay, so the idea when there's an addition or a subtraction of two terms, it will differentiate the terms individually and add, subtract their derivatives. Okay, so what this really means is if I have some function that's a function g plus a function h, then the derivative of f will be the derivative of g plus the derivative of h. Okay, and a similar thing if we're subtracting two smaller functions, then the derivative will be the derivative of the first one, subtract the derivative of the second. Okay, how does this look, I guess, in practice? If I have an example where my function is, say, 3x squared plus 5x, that one probably exists on the left, I'm not too creative, no, it's not there. So to differentiate this, I'll differentiate the first term, so I'll do 3 times 2x to the power 2 minus 1. And then I'll add on the differentiation of the second term. So remember that's really power 1. 5 times 1, x to the power 1 minus 1. And then I can simplify all of these. So 6 x to the power 1 plus 5 x to the power 0. And x to the power 0 is just 1, so it's just adding 5. Okay, so we need to know all our little index laws as well. Alright, so we'll turn over the page and we'll have a go at doing a whole heap of problems. I want you to have a go at these yourself first, and then, so press pause, have a go, and then I'll quickly go through these solutions. Alright, so I'll do these pretty quickly. If you've got any questions, make sure you ask them when you see me. Alright, differentiate following functions by rule. So I'll do all the steps. You might be comfortable skipping a step, that's fine. So I got x cubed, so my derivative, there's a 1 out the front, so I'll do 1 times 3, x to the power 3 minus 1. Okay, and simplify these terms, 3x squared. Onto the second one, this is a y equals, so when I differentiate, it'll either be dy dx or y dash. I'll alternate as we go through. Okay, coefficient times power, 4 times 2, and reduce the power by 1. Okay, so my derivative is 8x to the power 1, but I'm not going to write that power 1. Okay, another example, 3x, really has a power 1 here, so 3 times 1, x to the power 1 minus 1. So my derivative is 3x to the power 0. And I remember x to the power 0 is just 1. Okay, so my derivative is 3. This makes sense because 3x is just a linear function. Okay, so we know that the derivative is always going to be the same. So these ones with the power of 1, we know the derivative is always going to be a constant. Okay, we should be getting pretty good at these now. Okay, 8 times 5, x to the power 5 minus 1. I'll get 40 x to the power 4. Okay, so there's a negative number in front, but I'm not scared of negative numbers. I'm just going to do everything exactly the same. And I'm not scared of big powers either. Okay, so hopefully you're starting to see the idea how this rule applies. And imagine if you had to do this by first principles. At some stage, you would have to do f of x plus h and have minus 7 x plus h to the power 200. And you'd have to write x plus h 200 times and do that expansion. Okay, it'd probably take you 3 or 4 hours and you make heaps of errors. Okay, but with differentiation by rule, once we've established those general rules, we can just kick on and do it pretty quickly. Alright, here they start to get a little bit more interesting. Okay, what do we do when the x squared is on the bottom, the variable's on the bottom? Okay, we're going to just be a little bit creative and bring this x squared up to the top of the fraction line. Okay, so I'm going to change the power to negative and bring it on top of the fraction line. Notice that this is still y. Okay, this is really important. I haven't changed this to y dash or dy dx because I haven't yet differentiated. And now that I have this in the form k x to the power n, now I can differentiate. Okay, and when I actually differentiate, I'll then change it to either dy dx or y dash. Okay, and I'll just apply my differentiation rule exactly the same as I ordinarily would. So 3 times minus 2, x to the power minus 2, I need to subtract 1 from the power. Okay, so here I go, 3 times minus 2 is minus 6, and my power is going to be minus 2 minus 1, which is minus 3. Okay, and the general principle for these is that in my question, I was given it as a fraction with no negative powers, so my answer also needs to be in that form with no negative powers. Okay, so I want to change it back to look like the question. Okay, so same form as the question. Okay, let's have a go at this on yourself if you haven't already. Okay, but it's the same sort of idea, just different notation. Okay, my function is going to be 5x to the power minus 5. And bringing that x to the power 5 up top of the fraction line. And now I can differentiate it using my standard differentiation rules. Multiply the coefficient and the power. Okay, and reduce the power by 1. Okay, and then I want my answer to be in the same form as my question. Alright, some more interesting ones. When we have fractional powers, okay, like square roots, cubic roots, and we need to remember that this is really x to the power of a half. And now I can have a go at differentiating it. Okay, just using my differentiation rules as I would. Remember there's a 1 out the front here. So 1 times a half, and then x to the power a half minus 1. So my derivative is going to be a half, x to the power a half minus 1 is going to be minus a half. Okay, so generally don't like negative powers, so this whole thing is going to go below the fraction line. and I was given the question using square root signs, so I need to give my answer using square root signs. You might need to have a few goes at ones like these. Luckily there's a few examples. Okay, for example, cubed root. Okay, I can't do anything with a cubed root like that, so I'm going to have to x to the power of a third. So now I can differentiate, since I have it in that k x to the power n form. Okay, there's 1 out the front, but I'm not always going to write the 1. This third, so 1 times a third is a third. And I need to reduce the power by 1. So my derivative will be a third x to the power minus 2 thirds. Okay, should be comfortable with fractions by now. I'm not going to go through subtracting fractions. Okay, again, I don't like negative powers, so this x to the power to 2 thirds will come to the bottom and change the power to positive. And the question was given in square root form, so I'll give my answer in square root form as well. The number on the bottom of the fraction here, that 3, is always going to be the number root that we have. Okay, so it'll be 3 cubed root of x squared. Okay, alternative way of writing this could have been the cubed root of x squared. Okay, either way is fine. Okay, and you need to know that both of these work because you might need it for different reasons. Alright, so still some more square root ones, but it's okay, we should be pretty happy with these by now. 4 times square root of x, that'll be 4 times x to the power of a half. And now I can differentiate 4 times a half and reduce 1 from this power. So my derivative is 2x to the power of minus a half. Don't like negative powers. And my question was given with the radical, the square root signs, so I need to make my solution radical as well. Sweet, done. Okay, this is probably the hardest type of question there is, where I've got a fractional square root sign and it's on the bottom of the fraction. Okay, so I'm going to first just change that square root sign so that it's a fractional power. And then I'm going to make sure I bring this x to the power of a half up on top of the fraction line and make it a negative power. Okay, now that I've got it in that form, kx to the power n, I can go ahead and differentiate. So there's a 1 out the front, 1 times minus a half, minus a half, and x to the power minus a half minus 1. So what this will end up being will be minus a half x to the power minus 3 on 2. Okay. Don't like negative powers, so it needs to come below the fraction line. And I don't like fractional powers either. Okay, it sounds like I don't like a lot of things. So I need to change this x to the power 3 on 2 on the square root of x cubed. Okay, and make sure we carry down the f dash of x all the way. Okay, all these problems are pretty much the same idea. Okay, if there's a fractional coefficient, it's still all good. We'll just follow the same ideas. My k value is 5 on 7. My power is 4. I need to multiply them together. So 5 on 7 times 4, and then reduce 1 from my power. So my derivative, 5 on 7 times 4. Remember, this 4 is like 4 on 1, if you want to think of it like that. So I'm only multiplying the top line by 4. 20 on 7, x to the power 3. Okay. Even though there's fractions, okay, don't be scared, just apply the same rule as usual. Okay. Really giving you heaps of examples here. Keep powering through these. Okay, f of x equals 7. Whenever there's differentiating a constant, it's always going to be 0 because this function is just a flat line where the derivative is always going to be 7. Okay, sometimes the letters will be different, so instead of f's and x's and y's and x's, they're t's and r's. Okay, so to differentiate this one, we will be after dt dr. So the change in t and the change in r. But the process will be exactly the same. My variable is r. Okay, so it'll be the same idea. 8 times 1, r to the power 1 minus 1. This is power 1. So 8 r to the power 0, or just 8. And we can carry the dt dr all the way down. Okay, same, instead of f of x, okay, g of t, our derivative will be g dash of t. We can use all different letters for our variables. Okay, minus 6 to the power is 1, okay, t to the power 1 minus 1, and minus 6 t to the power 0, or just minus 6. Okay, try and get in the habit of writing the derivative in every step. If my function is a constant, even if the constant's 0, the derivative y dash or dy dx is still going to be 0. Okay, this one is just the line where y equals 0 on the x-axis. All of these points have slope of 0. Okay, now we have some addition differentiation rules. Now that we've practiced a few of these, we should be pretty good at it. So if I'm trying to find the derivative, I'm going to find the derivative of both of these and add them together. So 3x cubed will differentiate to 3 times, or 1 times 3, x to the power 3 minus 1. Okay, and we'll do the same thing here, 5 times 1, x to the power 1 minus 1. So simplify all of these. Okay, and remember x to the power 0, when we get there, x to the power 0 is just 1, so it's not going to be there at all. Okay, I expect that you can probably skip down to this step by the end of this lesson. Okay, we don't need to show all these details. In fact, for the next ones, I'm not going to show that level of detail. Okay. I'll try to differentiate this since they're all just individual terms which I can differentiate. Should be okay. So the first one, 4 times 2 is 8, and reduce the power by 1. So instead of x to the power 2, it'll be x to the power 1, but I won't write 1. Okay, next one, coefficient 5, power 5, so 5 times 5 is 25, x to the power, reduce this power by 1, and I know if I differentiate a constant, I'll just get 0. So I could write add 0, but I'm not going to. Okay, I don't need to. These last two are a bit more interesting in that you think, oh, this is interesting. Do I just differentiate these and multiply them together? Do I have some rule for multiplying and differentiating? No, not really. So before we can differentiate, we just need to change the form of this so that it looks like those other problems that we've done. Okay, now that I've expanded the brackets, I can now differentiate. Okay, remember, function, derivative. Only change it to a dash when we actually start differentiating. So I'll multiply a coefficient by power for x to the power 1, but I won't write that. And differentiating x, we're really just looking at what the number is in front here. Okay, there's a 1 in front, so it'll end up being a 1. Okay, if I'm differentiating 100x, okay, the derivative will be 100. So it's always just the m value in our mx plus c. Okay, this final example, again, division. I don't have any rules for division, so I'm going to have to be a little bit creative to turn it into that form. Okay, I'll see if I can find a common factor of x on the top. Okay, so I could say, alright, there's a common factor of x. I've got x squared plus x left over. And I could go cancel, cancel. So the function I'm really trying to differentiate is just x squared plus x. Okay, alternative way to do this is to say I want to divide both of these things by x. So I could write it as x cubed on x plus x squared on x. And I'd end up with, using my index laws, x squared plus x, exactly the same. Okay, so two ways to change this quotient, this division, into something more useful. Either way you want to go, our derivative will just be 2 times 1, and x to the power, reduce the power by 1, and the derivative of x will just be 1. And I don't need that power 1 there either. Alright, there's some questions there to have a crack at. Okay, have a go at those. Okay, have a go at those. There is some other questions that have some application to them. Okay, so this is exercise 13, what is it? I think 13E is just talking about some applications. Okay, but it's nothing different to anything that we haven't done already with rates of change. Okay, so you've got this situation, a javelin is thrown, so we know the height as the time changes. Okay, probably looks like this, the function. Okay, so find the rate of change of height at any time. This is asking us to find the derivative, okay, which we should be pretty comfortable doing after all those examples. To find that, okay, 20t, so that's just a linear term, 20. Differentiating something with a minus sign, it's okay, we can still do the differentiation. So minus 5 times 2, t to the power 2 minus 1, and differentiating a constant is just 0. So the rate of change of height at any time will be 20 minus 10t. Okay, so find the rate of change when t equals 1, t equals 2, t equals 3. It's asking me to find h dash of 1, h dash of 2, and h dash of 3. So substituting these 1, 2, and 3 into here for t. So 20 minus 10 times 1, okay, 10. 20 minus 10 times 2, oh, the rate of change is nothing there. Okay, and 20 minus 10 times 3, oh, the rate of change is negative. Okay, if I wanted to, remember I could check these on my graphics calculator. How would I do that? I'd go down into my graph menu, I'd graph this thing. Okay, hopefully I can see it there. Maybe do an auto zoom, and maybe then I could zoom with a box around the part that I'm interested in. Yeah, it looks pretty good. Yeah, remember, I need to go to menu, check that derivative is on. Yeah, I've got my graph, and I want to find the derivative, so I just need to sketch with F4, look for a tangent, and it'll tell me what dy dx is at any point. I could arrow across until I get 1, 2, and 3, or I could just type in 1. Give me a slope of 17. What have I done? Yeah, it doesn't give me a slope of 17. It says it's 17 meters high. The slope is this dy dx, which is 10, which is what I was after. What's the slope at 2? Yeah, the derivative is 0. And what's the slope at 3? Yeah, derivative is -10. So I didn't make any mistakes, which is good. Explain what's happening during the first 3 seconds of flight. So at t equals 1, slope is 10, so it's a positive. At t equals 2, the slope is 0, so it's flat. At t equals 3, the slope is negative, so it's downhill. Okay, so during the first 3 seconds, what we can say is that the javelin goes up, reaches its maximum height, and then comes down. Okay, and we can see that just by the slopes. What's the height of the javelin when t equals 2? Okay, so when it asks directly for the height, that's the original function. This h of t 20t minus 5t squared plus 2. Okay, asking us to evaluate the actual height. Okay, so it means substitute 2 into here. Okay, and let's just calculate a time. Try to do it without it like a big boy. Okay, the height will be 22 meters. Okay, now we can write that down there. Okay, so the purpose of 13e is really to make sure you know the difference between the original function, okay, that tells us the height, and this derivative function which tells us the rate of change of height, okay, so, or tells us the slope. Okay, so it's two different things. So h of t is the function, h dash of t is the slope, or the rate of change. Okay, that's the whole idea. Okay, there's some other questions there as well. Make sure you have a crack, and we'll have a look at all these sorts of things in class. All right.